Yeah, I'm ready when you are.
Perfect. So good morning, everybody from Canada. So my name is Hui, and I'm glad to coordinate the series on environmental and human health risk assessment series of the IIES. So today I'm glad to introduce to you Professor John Cherrie from Heriot Watt University and the Institute of Occupational Medicine. So today, Professor Cherrie is going to talk to us about the cancer risk from workplace and environmental chemicals. So he'll cover the second part of the risk assessment that is the aim of this series, which is on human health. So let me talk a little bit about Professor Cherrie. So he's currently a professor of human health at Heriot Watt University in the UK, and as well he is a principal scientist within the research division of the Institute of Occupational Medicine. He's graduated with a bachelor from the University of Edinburgh and a PhD from the University of Aberdeen, both from the UK. He's as well a chartered fellow of the Faculty of Occupational Hygiene, and just for information, it is the highest award that the faculty can bestow on a practicing professional hygienist. And before that, he held multiple other positions. We're just trying to summarize two of them here. He was a president of the British Occupational Hygiene Society, and he's a winner of the Bedford Medals of 2014. He is as well a very active member of the editorial boards for these journals that you might see the names here. He's author and co-authors of more than 200 articles, so likely 246 that I can count until now, 7 books and 27 book chapters. And I just want to share here the preface of a very successful textbook, Monitoring for Health Hazard at Works, which is one must read for occupational physicians, and I believe is translated into different languages. And so you may recognize his research interest area already, but I'm trying to show you 3 majors of them here. So the principal interest of Professor Cherrie is to understand the links between human health and exposure to chemicals, pesticide, asbestos, and other risk factors. He's working as well on the risk of occupational cancer, so I believe that he's going to be a part of the talk that he's showing us today, likely how to evaluate the risk of cancers from exposures to inorganic lead, tungsten carbide, and to workers who work in the rubber industry. And so the last but not the least is about occupational and environmental exposure assessment for epidemiological studies and modeling of exposure. So likely how to calculate and evaluate the risk of people to metals when they live in a contaminated land, and very similarly for pesticide. So I'm not going to hold you longer for that. I believe that we're all looking forward to the lectures given from Professor Cherrie. So I just want to thank you again, Professor Cherrie, for your kind acceptance to give this lecture to us. And thanks to you all for attending the lectures. So I just give the stage to you. Many thanks, Professor Cherrie.
Thanks very much. So I'm very pleased to be here to talk today, and hopefully you will be able to see my talk soon.
Yes, perfect.
Good. So as you've heard, I'm going to talk today about cancer risks from workplace exposures and from the environment. And I'm going to try and take a public health perspective on the issue. So I'm not really going to be so concerned about assessing risks in individual situations, but trying to understand what we know about these cancer risks across the piece in terms of risk to the population. Oops. Yes, works. So the talk will cover something about cancer and something about how the scientific community goes about trying to identify cancer hazards, particularly from chemicals, and that will rely very much on the epidemiological evidence and toxicology. We'll talk a little bit about workplace and environmental hazards, the various hazardous substances that might be important, and the environmental pollutants that are of interest. And then we'll talk about workplace cancer burden in particular, which is an important aspect of my research. and we'll consider the estimates that have been made of current burden and also future burden and interventions that might be taken to reduce future burden. So I'm going to take a very broad definition of what we mean by chemicals. So I'm going to include things which occur in workplaces, are important for carcinogens, for example, asbestos, diesel soot, and other things, which, as we'll see, make up an important part of the risks that people face. So just to set the scene a little bit, there are almost 10 million deaths every year that occur from cancer. That's about 1 in 6 of all cancers. All deaths are due to cancer. And this is a problem which is increasing. So in the future, we expect the incidence of cancers to increase globally, and in the next 20 years, it's predicted that there might be about a 60% increase in the incidence. This is partly because of changes in lifestyle factors, and also because everyone's having increased longevity, and cancer is by its very nature a disease of older life, and so if we live longer, then there's more likelihood that we'll have a risk of cancer occurring. The main causes of cancer are, main environmental causes of cancer are increased body mass index, poor diet, lack of physical activity, tobacco use, and alcohol use. And so these are the main things that make up probably 90–95% of the causes of cancer. Now, cancer is a disease of the developed world, particularly in Europe. And you can see the map of the world here, and the color coding represents the incidence rate mortality rate per 100,000 for all types of cancer. And the red shaded countries have the highest mortality rates, and the blue shaded countries the lowest mortality rates, and those with orange or yellow color are intermediate. And you can see, the rates are highest in Europe and in other developed countries in the northern hemisphere mostly. This is the pattern, and these are the mortality rates. If you look at the numbers of people who die from cancer, then it's predominantly the lower and middle income countries which are the source, and that's really because the bulk of the world's population is in countries like China and India and other parts of the developing world. Now, the main types of cancer that we're concerned about are breast cancer, lung cancer, prostate, bowel, and stomach, and then about they make up about half the incidence of cancer. Incidence is when cancers are first diagnosed. But clearly, we're also concerned about the ultimate effect and whether or not this causes mortality. And the pattern's slightly different when we consider mortality, and you see that lung cancer now makes up a bigger share of the overall mortality that occurs. And that's because although we've made great strides in trying to improve treatment for cancer, lung cancer is still a very intractable disease, and there's still a very high mortality rate for people who are diagnosed with lung cancer. Lung cancer is very important for occupational and environmental carcinogens because it's one of the key cancers which is caused by inhaling chemical and dust hazards. Now, the way that the international community identifies carcinogens is through the World Health Organization International Agency for Research on Cancer. And the IARC is the main international forum for this type of program. There are other systems which are in place. Some countries or other jurisdictions have methods to classify carcinogens, particularly the United States. But let's focus on this because it's certainly of international relevance. So they have what they call the monograph program, which regularly publishes monographs on the carcinogenic risks. These monographs are written by independent scientists, and they identify whether or not chemicals, mixtures, occupational exposures, physical or biological agents or other personal habits are risk factors for causing cancer. The assessment looks at the types of cancers caused by these agents, but doesn't quantify the degree of impact or the potency of the carcinogen. So this is really a program about identifying the carcinogenic hazards that exist within society. The approach that's taken is to rely on evidence from humans and from experimental toxicological investigations and some understanding of the mechanistic or other data that may support the evaluation. So the human evidence is primarily epidemiological studies, and the animal evidence is primarily experimental toxicological studies in rats, mice, or other species. At each stage, the evidence is evaluated carefully and would be judged to be of sufficient to sustain carcinogenicity, or of limited evidence, or inadequate, or evidence suggesting a lack of carcinogenicity, which is relatively uncommon. And then after each of these individual assessments is made, the overall evaluation is obtained by combining the evidence. And so if there was sufficient evidence in humans and in experimental animals, then the material, the exposure, would be classified as a group 1 carcinogenic agent. But if there's more mixed evidence, for example, there's sufficient evidence in animals but not in humans, then the assignment would be either probably or possibly carcinogenic in humans. To date, IARC have classified 120 agents as proven human carcinogens, and then about another 400 which are either probably or possibly carcinogenic to humans. There's only one which is classified as probably not carcinogenic, and that, I think, is primarily because the whole focus is about assessing things which might be carcinogenic, rather than that there are very few things which are not carcinogenic. Now, this graph shows the cumulative number of group 1 carcinogens that IARC has identified from the inception of the program until last year. And you can see it includes things like vinyl chloride monomer, asbestos, benzene, and finishes up with outdoor air pollution at the top of the list. And the important thing to take from this is that over this time period, there's a linear trajectory for these cumulative amount of carcinogens, which suggests that we are nowhere near estimating the total number of carcinogens that may exist in our societies, but really we are some way away from that, and that the identification of carcinogens is primarily limited by the availability of scientific evidence and scientists to evaluate that evidence. Now, in 1981, two very famous British epidemiologists were asked by the United States government to make an assessment of the preventable causes of cancer. In other words, things that we were exposed to in the environment which we could change that would allow us to actually reduce the incidence of cancer. So it was really very much about trying to identify what could be done to prevent cancer. And these two guys used very intelligent ways to try and understand that. For example, they contrasted the incidence of cancer in the lowest incidence areas of the world with the highest incidence areas of the world, and looked for the difference, and assumed that something in the differences between these environments might be the underlying cause. And then they evaluated the summation of all the other evidence, the epidemiological evidence and other information that was available. And what they concluded was that somewhere around about 75 to 80% of all cancers were potentially preventable. In other words, if we could alter the environment in which we live, then we would be able to remove a large proportion of the disease. And what they came up with were a list of what they thought were the best estimates of different contributing factors in the environment to the disease. On top of the list were diet and tobacco, and then infectious agents, reproductive concerns, occupational studies, geophysical, which they meant by ionizing radiation from radon and ultraviolet radiation from sunlight, and then alcohol, air pollution, and industrial products. Industrial products would be the part of this causal network which were from chemicals that we would use in our homes or which were in the environment. So you can see the things that we're dealing with in this talk, the preventable chemical exposures from workplaces and from outside or indoor pollutants, make up less than 10% of what Doll and Pito thought were the prime causes. Well, of course, this helped greatly in terms of framing public health policy in the 1980s, and it's interesting to see how things might have changed in the intervening time. So I've shown here some data from studies that have been carried out in the UK to look into this problem, and you can see that today the risks are not so very different in terms of the items on the list: tobacco, diet, etc., running down to other things like reproductive effects and so on. And if we compare these estimates with those of Doll and Pito, you can see that we now have less of cancer caused by tobacco and diet and infections, more which is attributed to alcohol and sun exposure, and then the others are all much of a muchness, not that much changed. If we add diet and obesity together, which may be quite reasonable, then that comes much closer to the original Doll and Pito estimations. Now, some of these changes have been because of changes in the society, so people smoke less tobacco, so one would expect there to be less contribution to cancer from tobacco in the UK and in North America. Some of it arises because of a better understanding of the risks that might take place. But the important thing, I think, to recognize for the things that we're interested in is that occupational exposures and well, they don't even consider air pollution as a cause here. These are all either about the same as before or a little bit less. Now, in terms of environmental carcinogens, many of the things that we saw on the list of items that IARC has evaluated are things that we encounter in our everyday life. And so, and preeminent amongst those are air pollution, because that is something that we're all exposed to every day. And air pollution is really probably the most important environmental carcinogen that we need to deal with. But other things like hair dyes, formaldehyde, arsenic, painting, house painting, have all been identified by IARC as carcinogenic exposures. The one thing that happens quite assiduously when things are identified as carcinogens and there's potential consumer exposure or environmental exposure is that we are very good at regulating these things. So, for example, carcinogenic hair dyes have been banned from use for many years in most developed countries. Formaldehyde is much more tightly regulated than it was previously. Now, there's still some uncertainty. So some of the items on that list are not definite human carcinogens, but are probable or possible human carcinogens. For example, the pesticide glyphosate is classified as probably carcinogenic, and acrylamide is possibly carcinogenic. Acrylamide is a chemical that is produced when we cook food at very high temperatures. Now, in most of these cases, the evidence is equivocal, and the exposures still occur, and there may be some risk associated with them. But overall, I think the important thing to recognize for environmental pollutants, other than air pollution, is that exposures are generally low, and they don't mostly occur continuously for consumers. They occur episodically. And for those reasons, the problems with most environmental carcinogenic agents is not great in terms of population risks. And that's something which is borne out by the evidence that we saw previously from the global estimates of cancer burden. Now, I want to spend a little bit of time on air pollution because I think in terms of environmental risks, it's probably the most important. The original suspicions about air pollution being a cause of cancer came from the 1950s, when there was a great deal of concern about high levels of pollution in some of our cities. And the 1952 London smog triggered a lot of concern about that, and many thousands of people died acutely because of the effects of this smog. Speculations about cancer were really primarily because of the presence of carcinogenic agents in outdoor air, for example, polycyclic aromatic hydrocarbons. And they observed difference in lung cancer incidence between urban and rural populations. Actually, that difference has turned out to be mostly explicable by differences in smoking patterns between people who lived in cities and those who didn't. But it really triggered concerns about the possible cancer risk. The main initial evidence to support the idea that outdoor pollution caused cancer came from two large US epidemiological studies that were published in the early 1990s. And these showed statistically significant associations between long-term exposure and lung cancer risk. And subsequently, there have been a number of studies, including very large studies in Europe, which have shown clear associations between outdoor air pollution exposure, particularly particulate pollution from combustion processes, and lung cancer. And in 2013, IIES identified outdoor air pollution and outdoor particulate air pollution as definite human carcinogens. As well as outdoor air pollution, indoor air pollution can be a problem, particularly in developing countries, and that primarily is from combustion of coal or wood or other biomass materials, either for cooking or heating. And if that's done in an uncontrolled way in indoor spaces, can give rise to very high levels of exposure and known carcinogenic risk. And for example, indoor combustion of coal is also identified by IIES as a carcinogenic situation. Outdoor and indoor air pollution cause about 25% of lung cancers, and the most likely contributor to that is the particulate fraction of the air pollution. You can see outdoor air pollution also causes other diseases like ischemic heart disease and stroke and chronic obstructive pulmonary disease. So the lung cancer is not the biggest contributor to that disease burden, but it's an important factor. And it's an important part of all lung cancers, which are caused by outdoor and indoor air pollution. And you can see that air pollution overall is number 4 in terms of the global contributor to mortality. And oops. All right. Apologize for this. It seems to have slipped. Yeah. It contributes about 400,000 deaths globally each year. There it is. In terms of risk, there's no evidence that there's a threshold in the exposure-response relationship for lung cancer from air pollution. And so this is a problem regardless of the level of exposure. So it doesn't matter if this is in China or in Canada or in the UK. There is some risk arises from outdoor air pollution. And every 10 microgram per cubic meter reduction in particulate matter less than 2.5 micron diameter could reduce lung cancer population attributable fraction by somewhere between 3 and 30%. Air pollution can also cause other, may also cause other cancers. In the original assessment by IARC, they considered that bladder cancer was possibly caused by outdoor pollution. Recent study failed to identify this association, but I think there's other reasons for thinking that there may be a small risk of bladder cancer associated with outdoor air pollution exposure. And there have been recent large epidemiological studies that have highlighted potential risks for breast cancer and for gastric cancer. Again, there needs to be further evidence to really properly substantiate these as being caused by outdoor air pollution, but certainly there's accumulating evidence. Now, there's some good news in all of this, and that in most countries, for most outdoor air pollutants, the concentrations are decreasing. So the graph shows data for London in the UK, for Thailand, the red line, and for China, 6 cities in China, for various indicators of particulate matter in the air. And you can see the longest series is for the London data, which goes back to the 1960s. And almost consistently throughout that time, the exposure or the concentrations have been dropping fairly steadily. And that's true in both Thailand and in China as well. The absolute levels are different in each of these countries, with the highest levels being in China, but the trends are similar in each situation. So although we have a risk of cancer from outdoor air pollution, the things we're doing to try and intervene to reduce pollution in our cities is having a demonstrable impact. Now, the next part of the talk is primarily about workplace situations, and in main part is about studies that have been carried out in the UK to try and update Doll and Peto's estimates from the 1980s to make them relevant to the 2010 and further on. The studies have been carried out to assess 2 things. First of all, the current burden, in other words, how much of cancer that we see today is caused by workplace exposures in the past, of course, and then how much of the future burden might be prevented if we do something to intervene. And so these 2 aspects are very important in terms of driving policy about risk management for carcinogens in the workplace. And the studies were funded by the regulator in the UK to help better understand what they could do. The work was carried out for IARC Group 1, these are the definite carcinogens, and 2A, those are the probable carcinogens, or other occupational circumstances. And the results show that different types of cancer have different associations with work. And so you see the first column, the blue and red columns, the blues for men, red for women, show that for mesothelioma, which is a tumor in the lung, which is caused by asbestos in the main, is almost always exposed, associated with work in men, and about 80% of these cancers in women are linked to work. The difference being between men and women that some women get the disease, in this case, from pollution, asbestos pollution, which is carried home by their partner to give rise to exposure in the home. So the next highest attributable fractions are for sinonasal cancer and then lung cancer. Lung cancer being third on the list, and we think that about 1 in 5 of lung cancers that occur in men are attributable to their past work. And then we have a whole host of other carcinogens, nasopharyngeal cancer, bladder cancer, breast cancer, and so on, that are attributable in greater or lesser measure to workplace exposure. Now, if we look at these data in another way, in other words, look at the number of, before I jump to that, overall, when we look at the total, about 5% of all cancers are attributable to work. Slightly higher in men, slightly lower in women, but around about 1 in 20 of cancers being attributable to their work. And as we saw from Dolan Pito's work in the 1980s, that's broadly the conclusion that they arrived at then. So although things might be improving in our general environment, it's not clear that things are improving in the workplace, or at least the evidence is equivocal about that. So we look at the evidence in a different way. Now we're looking at the number of cancer registrations that are attributable to different workplace exposures. So it's the same data, just switched around to look at the causal exposures. And here we see that more than 5,000 cancers, mesothelioma and lung cancer, are attributed to asbestos exposure. About 2,000 cases of breast cancer attributed to shift work involving night work. And then we have cancers caused by mineral oils, solar radiation, silica, diesel engine exhaust, and so on. And the important thing to come from this was that something like about 85% of all the occupational cancer cases that we were attributing came from the top 10 chemical agents. So although there may be hundreds of different carcinogenic materials used in workplaces, actually focusing on a top 10 would really focus efforts on the key causes of cancer in workplace settings. And this has been one of the main policy drivers that has come out of the studies. Of course, there is legislation to try and protect workers, and in Europe we've had specific legislation dealing with carcinogenic substances in the workplace since 1990. And each country in Europe enacts the legislation in their own way, in their own country, but there's a commonality between countries. One of the problems we've had is that since 1990, these laws have been virtually unchanged. There's been very little development, and the European Commission has tried to update things, and they started the latest updating in 2004, and we carried out the impact assessment to sustain the proposed changes in 2012, and it's only now in it'll be in 2019, 2020, when national governments get around to implementing these improved, updated changes. So legislation is fine, but it's necessary to have legislation to control carcinogens in the workplace. But in reality, it's not the main thing that protects people. Legislation, I think, you could argue, hasn't worked because, well, we still have 5% of cancers caused by work, which is, as we thought in the 1980s. The regulations don't include all the main causes of occupational cancer, so things like shift working involving night work are not included. Legislation in general is not very effective at instilling change in people. Updating the legislation has been a political exercise rather than a scientific or a policy initiative, and has been mired by the politics. And finally, people are although we've had this legislation for a long time, people in workplaces are generally quite poorly advised about what to do and how to go about doing it. Well, there is some good news, and the good news comes from this idea that things are improving generally. We can make change. So this is data from a PVC production plant, and you remember on the list of carcinogens that IARC had identified very early on, they identified vinyl chloride monomer as a known carcinogenic agent. And then in the early 1970s, scientific investigations identified that there was a risk of a very rare type of liver cancer that occurred in workers in these plants. And it was really quite shocking for the industries. I think, I've been told that, some companies considered just closing down their plants and retrenching from the production of PVC at the time, although that never happened. But what the industry did was invest considerably in trying to reduce the exposures. And so the graph shows over a period of about 2 or 3 years, the very dramatic reduction in vinyl chloride monomer concentration that was achieved in this one plant, dropping by more than an order of magnitude in that time period. And what did they do? Well, they did all the things that they were slowly trying to do anyway. They just accelerated the pace of change. So they introduced better cleaning systems for the production process. They improved the efficiency of the production to remove residual vinyl chloride monomer from the final PVC mix. They improved the ventilation in the factories. They introduced scale inhibitors that would make the cleaning easier. They took more precautions about opening up the batch reactors that they were using. And then they monitored the environment better to try and protect against leaks and other things. And then finally, if they had to enter areas where there were high concentrations, they used breathing apparatus to protect the individual workers. And that downward trend actually is remarkably consistent across different industries. So this plot shows data from different aerosols, metals, polyaromatic hydrocarbons, organic dust, and other things, all normalized to 1990, so that we can see the time trends for each of these. And this is on a log scale. So these are showing exponential decreases in concentration. And you can see that, for the vast majority of these data sets, there is a decrease in the concentration over time. Only in perhaps 1 or 2 of the data sets was an increase in concentration. So things generally get better over time. And typically, we would expect to see reductions in concentration of these agents, and most of them are carcinogenic agents, of the order of 5 to 10% per annum. So consistent reductions, which is partly to do with interventions in the workplace that are to protect the safety and health of the workers, and partly because of just improvements in technology. So sometimes replacing or improving the production process can reduce the exposures of individuals. And so there are a wide range of options of interventions that are available to regulators and others. You can look for ways to try and, as they did in the vinyl chloride monomer situation, accelerate the technological innovations. You can look for simple existing solutions that may occur. You can make appropriate use of personal protective equipment, or you can try some combinations of those types of things. And those are the practical things that can be done in the workplace. And the tools that are available to regulators are less direct, but they may be, for example, able to improve the compliance with existing legislation by increasing the number of inspection visits that occur, or they may be able to reduce exposure limits and hopefully then trigger further direct interventions by employers. Now, I thought it would be useful to give you an example to make this a little bit more concrete. This is one of the intervention scenarios that we evaluated for the future burden for the UK, and it deals with crystalline silica from things like construction processes, drilling, and other types of situation. Crystalline silica is sand, crystalline material that is liberated when you crush or drill natural rocks. In the UK, we had have a limit of 0.1 milligram per cubic meter of crystalline silica in the air. And the evidence base from research studies carried out in our country show that actually only about a third of workplaces comply with this limit, or complied with this limit, because these are historic data. So we set about trying to see, well, what would happen if we change things? For example, if we introduce new exposure limits, lower exposure limits, and we evaluated 2 limits, half or a quarter of the existing limit, and we also investigated whether or not improving the compliance, going from, say, a third of workplaces complying to 90% of workplaces complying, would that also have a benefit? Now, I realize this graph is really quite busy and there's a lot in it, so I'm going to just kind of step through and explain it in a bit of detail. So on the vertical axis, we show the number of incident cancer cases that occur that are attributed to silica exposure. And on the horizontal axis, there are time points, 2010, 20, right up to 2080. And each of these bars represents a different scenario. But the red bar represents essentially the baseline scenario. And you can actually see that at baseline, all the scenarios give an estimate of about 800 cases of cancer, lung cancer occurring because of silica exposure. Now, the red line is the baseline with the current situation. The orange is baseline at half the exposure limit, but still with only a third of workplaces complying. And the yellow one is a quarter of the limit with 33% in compliance. And then the green bars, the lightest green bar is this original limit value, but improving the compliance. And then we step through the lower limits with this high level of compliance again. So we can just maybe unpick this a little bit and look at the first set, which is really just the situation where we're reducing the limit. And so you can see it doesn't matter what happens, for the first 20 years, the number of incident cancers remains the same regardless of whether you have the 0.1 milligrams per cubic meter limit or you have the 0.025 milligram per cubic meter limit. That's because there's a latency period in terms of causing cancer. So it takes some time before any change that you see, the change that you make, producing any impact. But you can see from 2040 onwards, the lines start to diverge. And the baseline, which is doing nothing different from what we do today, would see a drop and then a slight rise again, back to almost where we started. And reducing the limit gives you some benefit. So by 2080, going to half the limit gives you about a 25% reduction in cancer cases, and a quarter of the limit gives you about half the incident cases. But the real benefit only comes if you get a better level of compliance with the existing legislation. So these are the 3 scenarios with improved compliance. And you can see by the time you get to 2080, all of these 3 scenarios give much reduced, almost all of them down to less than 10% of the original situation. And if you can get high level of compliance with a low limit, you could virtually eliminate this as a cancer risk. But it does take 40 or more years to achieve that, because of the latency that exists between the change that you make and the effect taking place in the body. So, you know, the question is, what could people do? And actually, there are lots of simple solutions that are widely available. So this is data from the US, or information from the US, that they explain to employers how to improve the way they do things. There are similar data available in the UK, and other data in the UK that are there already. They exist. They existed before the work that we had done. And these solutions can have quite dramatic effect. This is from the US, again, showing on the left-hand side a guy cutting out the cement between brick courses, so-called tuck pointing. And you can see he's shrouded in a cloud of dust, and the measurement, which is shown in this blue bar here, gives a value of 94 milligrams per cubic meter. As soon as you switch on ventilation, which is on the equipment that he's using, then you get this situation on the right-hand side, no sign of any dust cloud, and the measured value is more than almost 100 times lower than the original. So these are solutions that have been around for years, and what we need to do is try and get more employers to take them up. In addition to that, we promote the idea that we need to improve the use of respiratory protection, which can be a very effective way of reducing exposure where other approaches may not be practicable. So where you have, for example, traffic policemen who have to work in city streets, this may be some option that we should be looking at. So in terms of workplace carcinogens, I think the bottom message that we have is that we can't have status quo. If we stay the way we are, then in 30, 40 years' time, somebody else will be coming along and saying, well, 1 in 20 of cancers are all caused by work. Or maybe it'll be a higher proportion. If we are successful in reducing the cancer burden from other causes, then work may actually end up being more of a problem than we thought. And what we need to do is try to accelerate the process of continuous improvement that already exists, to try to improve the situation, and to take care not to allow new carcinogens to enter our workplaces to balance up any reductions that we're achieving. So in conclusion then, a summation of all the things that I've been talking about, I think we need to better understand carcinogens in the workplace. The evidence that we have is that it's a relatively small number of carcinogens that make up the majority of the burden that occurs. That wasn't known until after the studies that we carried out, and that's been an important way of focusing attention on the most important risks that occur. Same's true in the environment, that we need to have better information about the levels of exposure and how we could improve them, both for air pollution and for other potential carcinogens that we may have in our society. We need better legislation. Well, legislation is necessary, I think, and in the workplace, it does provide minimum standards that we might achieve, but on its own, it's not sufficient, and we need to look at other ways to engender change in workplaces to make things better. And one of those ways is to try and build coalitions between different partners in the workplace and in society, people who are responsible for the risks, like employers or polluters, and those who are experiencing the risks, like workers and people in society, and try to get everyone to work together in a more focused way, informed by the science, to try and tackle these problems. Evidence says that things are getting better, both in the workplace and outside the workplace, but we could do better than that. And I think that's what we would like to see, is an improvement in the way that things are done in both situations. And it's not as if we have to invent new solutions. There are already existing solutions for everything we want to do. We just need to try and find ways of accelerating their application. Okay, well, thank you very much. I'm more than happy to take any questions if there are any.
Awesome. Thank you very much, Professor Cherrie, for this very interesting talk. So we should improve greatly our working conditions, right? So simply maybe follow all the rules that we may have in the lab. So just very important. So it may be some questions from the audience. So I might just start first, so give the audience some time. So for the particulate matter concentration in the air, you say that the decrease overall in the world, but is that the average trend of the year, or is that and how about the seasonal variation of that? Because
so these are generally annual average concentrations, or so seasonally there can be very big differences, and if you live in China, then the pattern of pollution through the year changes very much depending on the season. So it may be that in the winter time there's more pollution because of heating, and other times of the year wind-blown dust may be very important. And in some parts of the world, in Southeast Asia particularly, then, well, I'm saying particularly, but actually in California, there's been recent examples as well, where in the dry season, there may be burning, either deliberate burning or accidental burning, that increases the pollution levels quite dramatically. And I honestly think these are big issues to be resolved, both deliberate burning of crop residues to clear the land for next year. We can find better ways of doing that, and better management of our wild areas to try to reduce the risks of forest fires that occur accidentally would be beneficial, I think.
Yeah. Of course, yeah. And I see that there is as well quite of, regarding that, there is quite a quick responses from the regulation for that, for example, right? I mean, in Paris, for example, they monitor that, and then they just introduce an alternative circulations of car depending on your license plates, something like that. But I mean, it is not for everything, right?
No. And, I think, managing traffic flow or using face masks are good ways to try and deal with short-term fluctuations in concentration. But what you've got to recognize is that the cancer risk from pollution is not to do with short-term exposures or even episodic exposures. It really is about the long-term average exposure over a person's lifetime, probably, that determines whether or not they will get cancer from the environment or from their workplace exposures.
I see, yeah. Perfect. Thank you very much. There's any questions from the audience? Okay, I just go with another one though. It's very interesting. Yeah. Could you please elaborate into the connections between shift works and cancer? Because I mean, it's not very straightforward to see these connections because of the fact that you work in nighttime and then you got cancer by the.
Yeah, no, I mean it's a very controversial topic, and the underlying science suggests that working at night, which is unusual for all of us, disrupts our natural circadian rhythm. And these rhythms are dictated to a large extent by diurnal fluctuations in our hormone levels. And a number of cancers are known to be caused by hormonal mechanisms. And so it's hypothesized that these disruptions of our hormone levels are triggers for risk of cancer. And so the prime focus has been on breast cancer in women and night work amongst women. Now, the original evaluation was carried out by IIES about 10 years ago, and they concluded that there was a possible risk that, a probable risk that night work involving circadian rhythm disruption was carcinogenic. And that was in part based on evidence from animals, in part based on evidence from humans. But the problem is the human evidence was rather weak in terms of the associations. Since that evaluation, more and more evidence has accumulated, and we're now in a position to take a better view about that. And we just published this year a review of the epidemiological evidence, and we concluded that the magnitude of the risk has dropped in more recent studies, and it may not be increased at all. And next year, IARC will have another monograph meeting where they will again review the evidence and come to a decision. So I think the jury's still out in terms of whether or not there is a risk of breast cancer from shift work, but the more definitive position will come next year from the IARC evaluation.
Awesome. Yeah, thank you very much for the information. We may have time for one last question from the audience, if there's any. Okay, or if not, just please send me your question through email, and I was glad to transfer to Professor Cherrie, and then could got answers from Professor Cherrie. So
yeah, I'd be very happy to answer any questions that people have after the lecture.
Awesome. So again, many thanks, Professor Cherrie, for this very wonderful talk, and thanks to all of you for attending the lectures.
Thank you.
Have a good day. Thank you.
Bye-bye.
Bye-bye.